Hi everyone, I and Siddharth are going to present today on the vision transformer with linear multi-head self-attention using Nystrom method for matrix approximation. Next slide. Using standard transformers for vision-based applications like image classification is highly inefficient because images, when unrolled, have long sequences of pixels, making the model slow because of the quadratic complexity of matrix multiplication operation. Also, it becomes impossible to utilize image properties such as translations and rotations in transformers, unlike in the CNNs. Through this work, we build a highly efficient vision transformer model having self-attention with linear complexity, which uses long-term dependencies of image pixel sequences and the dynamic weights for image classification. The proposed linear model focuses leveraging Nystrom method of matrix approximation as an improvement over traditional vision transformers to approximate the self-attention mechanism by reconstructing the softmax matrix utilizing landmarks or the Nystrom points on the complex ImageNet dataset. Next slide. So in the original vision transformer model, to calculate self-attention, first we had to compute the cosine similarity between query and key matrix. This is done by calculating the dot product of Q and K matrix requiring n square matrix multiplication for a quadratic time complexity. The proposed algorithm guarantees linear space and time complexity by removing the need to calculate each and every element of the self-attention matrix. So once query and key matrices are computed, we calculate Q and K tilde matrices using an intelligent subsampling of n by n elements. We calculate only m Nystron points out of n total sequences, and if m is much smaller than n, then linear complexity is achieved. This is an improvement over the original vision transformer model as well as the original Nystrom approximation model. As in the original model, the matrix was sampled after the final softmax operation, leading to quadratic time complexity. So our proposed sampling technique performs partwise averaging of equal segments. This will result in sampling only m points from n sequences, with each point being an averaged representation of m segments as shown by the formula here. Pseudo Penrose inverse of approximated softmax matrix is calculated with the help of singular value decomposition. Hence, our architecture replaces the quadratic attention in VIT with the linear attention, thus achieving faster speeds and convergence while working with long sequences of image data. Next, Siddharth is going to go through the results.
So to compare the computational complexity and inference speeds of our proposed linear weight with the original weight architecture, we performed several quantitative experiments on the ImageNet 1K dataset, whose results we have on this slide. So first table compares the total number of trainable parameters and multiplication, addition, accumulation operations required for a single forward pass for both the architectures. It is evident that our method reduces the overall parameter size by 87% and the computational complexity by 85%. Similar trend is observed in the overall architecture, where the end-to-end model required 40% less parameters and 41% less maps compared to the original baseline weight. The reduction in the model size did not lead to any classification performance loss, as evident from table number 3. So proposed weight matched the classification accuracy by achieving 48.9% of the validation set, whereas original weight achieved 48.1% after 30 epochs of training. So in terms of the convergence speed, on an average, per epoch training time was approximately 20% less for our proposed model. Similarly, the inferencing time for proposed model is faster by about 23 milliseconds for a single input image, as shown on the table. So we also compared the training and validation statistics for both of these models for a setup of 30 epochs. It is clearly evident that the training loss as well as the validation loss for proposed model remains lower for the majority portion of the training process, with the gap being narrow at the 30th epoch end. Similar trend can be translated for training as well as validation accuracy. One key thing to note that is objective function is not converged based on the curves. Therefore, training the models further can be a good future direction to identify the performance difference and trade-offs between the two methods. Thank you.